Hello everyone. In today's class we are going to study graph coloring problem by making use of backtracking method. So first let us understand what this graph coloring problem is. So here is the problem statement. Given an undirected graph and a number m, determine the graph can be colored with at most m colors such that no two adjacent vertices of the graph are colored with the same color. Here we are having one graph which is undirected graph and we will be given with some number m. Okay, so we have to determine the graph which can be colored by making use of those m colors in such a way that there is a condition no two adjacent vertices of the graph are having same color. So this problem is also called as m colorability decision problem. Here coloring of the graph means assignment of colors to all the vertices. So if the degree of the graph is d, then we are going to have d plus 1 colors which are used to color that graph. M colorability optimization problem finds the smallest integer m for which the graph G can be colored. So that is called as chromatic number of the graph. Okay, here is an example. 3 colors are sufficient for this graph to color. Okay, hence that 3 is the chromatic number for this graph. So which is the minimum number of colors we are going to use in order to color this graph. So where no two adjacent vertices are having same colors, that number is called as chromatic number. So here in order to solve this graph coloring problem, so we have to represent the graph by adjacency matrix which will be n cross n. So colors are represented as 1, 2 and 3 so on up to m. Solutions are given as a n tuple x1 to xn where xi is the color of the node I. So here in order to have the solution we are having one vector array, so where these all the colors are stored. So here is an algorithm in order to find the colors for the graph. So here this algorithm is going to start with a method that is m coloring method. So here k is the index of the vertex which is to be colored. So this algorithm was formed using the recursive backtracking schema. The graph is represented by its Boolean adjacency matrix n cross n, that is G of n cross n. All assignments of 1 to m to the vertices of the graph such that adjacent vertices are assigned distinct integers and which are printed. K is the index of the next vertex to color. So here if you want to color first vertex, then k value will be 1. So this we are going to repeat in order to generate colors for all the vertices. So here one more method we are using, that is next value. So this is used in order to find the color for that particular vertex k, and it is going to check the conditions whether two adjacent vertices of this k are having same color or what. So that is where it is checked in this next value method. So here generate all legal assignments for x of k, and this next value method is going to assign legal color to the x of k. So that is what the entry. So this is the vector where we are going to store the color numbers for the vertices. Okay, so then this, when we call this next value, it is going to assign a valid number to that particular vertex. If it is not finding any of the valid color to assign to that particular vertex, then it is going to assign 0 to that particular vertex. So that is what we are checking here. If x of k is equals to 0, then it is going to return. That is what? No new color possible for that particular vertex. So this is the condition to check that whether this next value assigned 0 to that particular vertex or what. Okay, so then if k is equals to n, okay, that time means what, this k has reached to the last number, so then which is equals to total number of vertices. At most m colors have been used to color the n vertices, means we are at the end. All the vertices are assigned with a color. That time k will be equals to n. So then we are going to output that vector, color vector. So that is what, write x of 1 to n. Or else if there are some more vertices which are remain to be colored, so then again this m coloring method is called with a value next value of k. So that is k plus 1, means second vertex color is to be found. Okay, so then so this is done until the loop becomes false. So this will be repeated until all the vertices are going to get the color. Next we'll see this next value, how it is going to assign the color to the particular vertex k. So here is the algorithm of next value k. X of 1 to x of k minus 1 have been assigned integer values in the range 1 to m such that adjacent vertices have distinct integers. So here, if suppose we are given with a m as 3, then the range between 1 to 3 only will be assigned to the vertices, and such that adjacent vertices have distinct integers, means distinct colors. A value for x of k is determined in the range of 0 to m. Next, x of k is assigned the next highest number color while maintaining the distinctness from the adjacent vertices of the vertex k. Okay, so here first we are going to start with a 1, number 1 for first vertex. So then next highest number of 1 is 2. So we are going to start 2, assigning 2 to the second vertex. So this is how it continues. Next highest numbered color is taken and it is checked against distinctness. Okay, if no such color exists, then x of k is 0. So what happens if we don't have valid colors to assign to that particular vertex? So then this next value method is going to assign 0 to this x of k, and previous to this all the entries of this x array are assigned with a value 0. That this x array is initialized to 0. The logic here is, for a vertex, start coloring from 1. If the adjacent nodes have same color, keep incrementing till m. Okay, if the adjacent matrix are getting same color, then increment the value and then check. So here is the condition. We are going to start from first vertex, that is x of 1. Okay, so initial value of x of 1 is assigned to 0. So that is 0 plus 1 is 1. Mod m, if suppose we are given with 3 colors, that time m is 3, that is m plus 1 is 4. Okay, 1 mod 4 is 1, hence 1, the value 1 is assigned to x of 1, means first color is assigned to first vertex. So then we are going to check if x of k is 0, means there are no colors. Okay, so this condition is also checked. If that is the case, we are going to return, but here it is not 1, hence we are not going to return. We are continuing with this for loop. Here we have written one more for loop to check the conditions for adjacency matrix coloring. Okay, so this loop is going to iterate from 1 to n, where the condition for adjacency is checked. Here g of k comma I is not equals to 0, then we are going to check x of k is equals to x of j. So here this is nothing but this is an edge, that is k comma j. Here g of k comma j, which is not equals to 0, means there is an edge between k and j, means they are adjacent. So this is where it is going to represent this as a adjacency vertices. These k and j are adjacency vertices because they are having edge between them. When they are having edge between them, the value in the adjacence matrix will be 1, okay, which is not equals to 0. So this whole condition means k and j are adjacent vertices. So if they are adjacent, then we have to check whether x of k is equals to x of j, means are they assigned with the same color or what? Here x of k is what? 1 we have just now assigned. Then x of j is initialized to 0. Hence 1 is not equals to 0. Hence we are not going to terminate this for loop. If whenever they are adjacent with each other and are having same color, this for loop is going to terminate. So that is where we are going to assign the previous node with a different color. Okay, hence this condition is going to check the color of the adjacent vertices are having same or different. Yes. Now it is going to repeat for all the vertices. Okay, at the end, if this for loop ended properly, so then j will be having the value of n plus 1. So that time we are going to return. Otherwise, if with the adjacency vertices having same color, so that time it is going to terminate. This for loop is executing this break statement and it is going to terminate. That time j will not be having n plus 1. Okay, so that time what we are going to do, we are going to try with another color. Okay, otherwise we are going to return this value to the m coloring method. So otherwise we are going to try with the next color. So this is how the next value method is going to return the value here, where again here it is checked whether the possible color is there or not. So then all the vertices are colored or not. If they are colored, then we are going to return the output. We are going to write this output. So this is how the algorithm of graph coloring works. Here is an example. We have a graph with 4 vertices and we have given 3 colors to color the vertices of this graph. So this whole problem, this state space tree shows the all possible successful coloring. Okay, where these nodes are called as promising nodes because they are leading to the proper solution. Here, if we start with the first vertex, that is k equals to 1, and we are having 3 colors. Hence, so there is a possibility of assigning 1 and 2 and 3 colors to this first vertex. Hence there are 3 possibilities. 1 can be assigned, 2 can be assigned, and 3 can be assigned. If 1 is assigned with the assigned to first vertex, then what we are going to assign to this second vertex. As 1 is adjacent, we cannot assign color 1. Hence we have a possibility of assigning 2 and 3 to this second vertex, that is x2. Okay, if we have assigned 2 color to this second vertex, what can be assigned to this third vertex? As it is adjacent vertex is having 2, we can assign either 1 or 3 because 1 is not adjacent to 3. We can assign 1 and one more remaining color is 3. So either 1 or 3 can be assigned to this third vertex. If we have assigned 1 to this third vertex, we cannot, as both the adjacent vertices of this 4 are having same color, that is 1 and 1. Okay, so then we have 2 more colors remaining, that is 2 and 3. So there is a possibility we can assign this 2 and 3 to this fourth vertex because both the adjacent vertices are having 1 and 1. Okay, so hence 1 we cannot assign and 2 and 3 can be assigned. Same thing, if this third vertex is assigned with a third color, we cannot assign third color to this fourth vertex because 3 is having third color and 1 is having first color. Hence 1 and 3 are not assigned. Hence the vertex 4 can be assigned. So this is how we can solve the graph coloring problem. Thank you.